Hi everyone, so in this video we continue with Chapter 7, Geometry and Trigonometry. Specifically Section 7.3, Trigonometric Functions of Any Angle, and we are going to delve into defining trigonometric functions for any angle in standard position. So if you have an angle in the Cartesian plane, as you can see here, and it is defined by a point P with coordinates x, y, we can draw from the origin a line, as you can see here, a line going through those points. If we draw another line that is perpendicular to the x-axis, we are going to have, as you know, a right triangle. And from this, we can determine that the height of this triangle has to be the same as the y-coordinate, and the base of the triangle has to be the same as the x-coordinate. So notice that from this we can derive trigonometric functions. So sine should be y over r, cosine should be x over r because x is the adjacent, and tangent would be y over x. One thing that they're not mentioning here is that r, because it's a hypotenuse, r would equal the square root of x squared plus y squared. So we begin with example 7.10, and they ask us to find the sine, cosine, and tangent of an angle alpha that contains the point -3, 4 on its terminal side when in standard position. So remember that with this, we always use a right triangle as a reference. So this is our right triangle, and this is, by the way, our angle of reference as well. We're not going to need this angle of reference for now, but it's good to indicate it. So this here is -3. This distance here is -3. This is because we are in the second quadrant. So the x values are negative. 4 would be the y value, which is positive, and we need r. But again, r, as we said before, is the square root of x squared plus y squared. So r here is going to be square root of -3 squared plus 4 squared, and this is going to give us 5. So this is 5. And with this we can find all the ratios, because that means that sine of alpha is going to equal 4 over 5. And this makes sense because sine is positive in the second quadrant. Cosine of alpha is going to be -3 over 5. And tangent of alpha is going to equal -4/3. So on the next slide, we see a summary of the previous situation. So notice that this is the terminal side here with the point -3, 4, and this is angle alpha, where theta would be our reference. So this is our reference triangle, which we can see right here with sides 3, 4, 5, and the angle theta. Now recall that we have different signs for the trigonometric ratios depending on the quadrant in which they are. So in quadrant 1, remember that all of them will be positive, sine, cosine, and tangent. In quadrant 2, sine is positive, cosine is negative, and tangent is negative. In quadrant 3, sine and cosine are negative, therefore tangent would be positive. And then in quadrant 4, we would have that sine is negative, cosine positive, and therefore tangent negative. We continue with example 7.11. Find the sine, cosine, and tangent of the obtuse angle that measures 150 degrees. So 150 degrees is 30 degrees away from the x-axis. Don't forget that the x-axis is always your reference. Don't use y, it's always x. And in this case, our reference angle is the 30-degree angle. So let's go to the special right triangle where we have 30, 60. So if this is 30 and this is 60, Remember the proportions. This is going to be 1, the hypotenuse is going to be 2, and this is going to be square root of 3. So this is our reference. Now remember that sine of 30 is equal to 1/2. Cosine of 30 is equal to square root of 3 over 2, and tangent of 30 is equal to square root of 3 over 3. But this is not the answer because this is our reference angle. So all we have to do is think about what is positive and what is negative in the second quadrant. So remember that you can use x and y as a reference. So remember that x would be our cosine. That means that cosine should be negative. Also, y is a reference for sine, and in this quadrant, it's positive. And then tangent, remember, is sine over cosine, so it should be negative. Therefore, we can conclude that sine of 150 is going to be the same as sine of 30, which is 1/2. Cosine of 150 would be negative square root of 3 over 2, and then tangent of 150 would also be negative, but negative square root of 3 over 3. We continue with example 7.12. And it says, given that sine of theta equals 5 over 13, and that theta is between 90 degrees and 180 degrees, find the exact values of cosine and tangent of theta. So the key is this right here, because this tells us that theta is in the second quadrant. So if we think about it, it should be somewhere around here, let's say. And this would then be angle theta. Our reference triangle would be, of course, this one. And because they're telling us that sine is equal to 5 over 13, we use alpha as a reference. So sine is opposite over hypotenuse. So that means that this is 5 and this is 13. So we still need to find our x coordinate, which, by the way, must be negative. So what is x? X would equal, using Pythagoras, the square root of 13 squared minus 5 squared. And this is going to equal 12. Okay, so that means that this coordinate here for x should actually be negative 12. Negative 12. So once we have that, we can simply write the values for cosine and tangent, because then cosine of theta would equal negative 12 over 13, and then tangent of theta would equal negative 5 over 12. All right, so we continue with example 7.13. And they ask us in A to find the acute angle with the same sine ratio as 1, 135 degrees, and 2, 117 degrees. So let's focus on letter A. So when is sine going to have the same ratios? Well, in this case, because these are positive angles, let's think of it as this. So let's start with 135 degrees. So let's suppose that this is 135 degrees here. 135 degrees. So when they talk about finding the acute angle, it means here in the first quadrant. Then our reference is going to be this guy over here, right? So the mirror image of that angle would be here. So this is what we really want to find. But it's easy to find, because it turns out that sine of 135 is equal to sine of 180 minus 135. And this is going to give us 45 degrees. So it means that for sine of 135 is equal to sine of 45, and this is our acute angle. Likewise, sine of 117 is going to equal sine of 180 minus 117, and that is going to equal sine of 63 degrees. So these would be our solutions for sine. Okay, so let's focus on cosine. To do that, let's get rid of all this, and let's work on B, where they say find the acute angle. So that again is going to be here in the first quadrant with the same cosine ratio as 300 degrees. So where's 300 degrees? Well, more or less here, more or less there, okay? So if this is, all of this is 300 degrees, remember that our reference angle is this one. And also remember that cosine is positive here and also positive here, because our reference for cosine is x, right? So really they want us to find this angle. So how do we find it? Well, simply go 360 minus 300, and that equals 60. So that means that cosine of 300 degrees is equal to cosine of 60 degrees. And with 342 degrees, we would do exactly the same thing. So we would say that cosine of 342 has to be the same as cosine of 360 minus 342. And that means that cosine of 342 is equal to cosine of 18. Very well, so the next slide is about areas of triangles, and I'm going to show you how an interesting formula is derived. So let's look at this acute triangle here to the left. We know that the area of a triangle is equal to 1/2 base times height. But if we draw a height in an acute triangle, notice that it forms two right triangles. So what if we put h in terms of angle C? What do I mean by that? Well, notice that sine of C is equal to h over a. In other words, h is equal to a times sine of C. So if we plug this in here and we substitute for h, we have a different expression. And that would be 1/2 b times a sine of C, which normally would be written in alphabetical order. So it equals 1/2 a b sine of C. So that means that for any triangle, if I have sides A, B, and angle C contained between them, I can use this formula. But how about in an obtuse triangle? So this is the case of an obtuse triangle. So again, remember that the area of any triangle would be 1/2 base times height. Okay, but we can express the height here in terms of this angle here, which is 180 degrees minus C. So we know that the sine of 180 minus C is equal to h, the opposite, over a. Again, that means that the height is equal to a times sine of 180 minus C. But we know from the properties of sine that sine of 180 minus C is the same as sine of C. So we end up with the same formula. We end up again with 1/2 AB sine of C. So that means that this formula holds true for an acute triangle or an obtuse triangle. Okay, so next we have example 7.14, which shows a circle that has a radius of 1, a central angle theta that subtends an arc of length 2 pi/3 centimeters. So this is the arc and its length. Find the area of the shaded region, which is a segment of the circle. Okay. Okay, so this is the area they want us to find. These problems where they want us to find a segment like that normally involve subtracting the area of the sector minus the area of the triangle itself. The area of a sector, if you can recall, is equal to 1/2 r squared times theta, where theta has to be in radians. And in this case, we need to use the formula for the area of a triangle that we just studied, which was, as you recall, 1/2 a times b times sine of c. Now c would also be, in this case, theta. So from these two formulas, we can see that we need to find theta because it doesn't indicate what theta is in the diagram. One thing we can use is the fact that we know that the arc length is equal to the radius times the central angle, and this in radians again. In this case, we know that the arc is 2 pi thirds and the radius is 1. So 1 times theta should equal this. That means that the angle itself, because the radius is 1, is 2 pi thirds. So then the area of that shaded region that we want to find would equal 1/2 times 1 squared times 2 pi thirds minus 1/2 times a times b times sine of theta, or sine of 2 pi thirds. Now you have to make sure your calculator is in radians when you do this. So this will equal, for this part here, this will equal pi thirds minus, and this part here will equal square root of 3 over 4. And then this can equal 4 pi minus 3 square root of 3 over 12. So this would be the answer. This would be the area of the shaded region. And this equals approximately 0.614 centimeters squared, which is the unit. And notice that this is rounded to 3 significant figures. Okay, so next is example 7.15, where they say, show that it is possible to construct 2 different triangles with an area of 35 centimeters squared that have sides measuring 8 centimeters and 13 centimeters. For each triangle, find the size of the included angle between the sides to the nearest tenth of a degree. Okay, so what they want us to prove is that this triangle and this triangle can have the same area. All right, so for this we're going to use the formula that we learned earlier, which is that the area of a triangle, that is, if you have the angle included between the sides, right, is going to be 1/2 AB times sine of the angle. So sine of C normally, right? But in this case, we're going to say sine of alpha. Sine of alpha. So that means that 35 must equal 1/2 times 8, which we call A, times B, times the sine of alpha. Okay, so then that means that we have that 35 is equal to 52 sine of alpha, and we can find alpha because alpha is going to be equal to the inverse sine of 35 divided by 52. So here we have to plug this into the calculator, and since they want the answers in degrees, it has to be in degrees. So this is going to give us approximately 42.3 degrees. So that means that alpha is 42.3 degrees. So this proves that this angle is 42.3 degrees. But what would this angle be here in order for these two triangles to have the same area? Now notice that this is an obtuse triangle. Obtuse triangles are over 90 and obviously less than 180. So that is the same situation as having sine here and sine there. So that means that beta would necessarily be equal to 180 degrees minus 42.3 degrees. And this is equal to 137.7 degrees. How can we prove that this is true? Well, if we find this area for this triangle, and it turns out that it is equal to 35, then we would be proving that there can be two triangles with the same area, right? Okay, so let's do that over here to the left. And we are going to say then that 35 should equal 1/2 8 times 13 times the sine of 137.7. So we plug that into the calculator, and we are actually going to get a number that is very close to 35. Now, obviously, we are working with approximations. So you might get 34.999996 or something like that. So in conclusion, we can say they have the same area. Very well, so the next topic that we're going to cover are equations of lines and angles between two lines. So take a look at this graph here on the left. Notice that this line has this equation, y equals 1/2 x minus 1. So they might ask you, what is the measurement of this angle theta that the line is making with respect to the x-axis? So what is this angle theta? It turns out that we can use the slope of the angle. Why so? Because the slope of the angle is a ratio, and it's the ratio of y over x, right? Vertical change over horizontal change. Now remember that is related to the tangent function. So we can use inverse tangent of the slope, as indicated here, to find an angle that is formed between, say, the x-axis and a line. So then, notice that since the slope of this line is 1/2, and the inverse tangent of 1/2 is 26.6 degrees, that means that theta here is equal to 26.6 degrees. Now, in the case to the right, we have something very similar, but we're going to get a negative angle, negative 26.6 degrees. And why is that? Well, because first of all, the angle is measured clockwise, and please remember that these angles are always in negative values. And then the slope is also negative. So if we do the inverse tangent of negative 1/2, it gives us negative 26.6 degrees. Very well, so now we will apply this to example 7.16. And here they say, find the acute angle between the lines y equals 3x and y equals negative x. So when they talk about the acute angle, sorry about the thundering, guys. It's going to be all over the recording, but it's raining, okay? The rainy season is here. So then, what they want us to find is the acute angle. So that means that they want us to find theta. But by using the inverse tangent, we're going to find actually alpha and beta. Alpha and beta. So let's start with that. Okay, so we know that alpha is going to equal the inverse tangent of the slope of that line, right? 3x. So that means the inverse tangent of 3. And here we're going to get approximately 71.565 degrees. That's the measurement of angle alpha. For beta, we do the same thing, inverse tangent of the slope of the line, which in this case is -1, and this will be negative 45 degrees. But these measurements don't help us right now, right? Because what we need to find is theta. Okay, Theta is the acute angle, but the obtuse angle, because lines will make one obtuse angle and one acute angle, unless they're perpendicular. So the obtuse angle is going to equal alpha minus beta. Now you might say, why minus? Well, because beta is negative. So this is going to equal 71.565 minus 45. So that means plus 45 is going to equal 116.565 degrees. So we are ready to find theta, because theta is simply 180 minus that. So 180 minus 116.565 is going to equal approximately 63.4 degrees. Remember, to three significant figures. Next we have example 7.17. Find the acute angle between the lines y equals 5x minus 2 and y equals 1/3 x minus 1. So these two lines are a little bit different from the previous examples in the sense that they don't go through the origin. They don't go through here. So we have to use as a reference their point of intersection, which is this one right there. At that point of intersection, we can draw an imaginary line and realize that with reference to this line is that we're going to find those angles. Now that doesn't change anything at all. We're still going to do the inverse tangent of the slopes. Notice that if I want to find angle, say beta, this small one over here, it's still going to be tangent of the rise over run. And likewise with the other one, with angle alpha, also it's going to be rise over run. Only notice that this has a long rise and a short run. So let's find first of all alpha and beta. So alpha is a large angle. That means that alpha is equal to the inverse tangent of 5. And in degrees, that is approximately 78.690 degrees. Likewise, if we do beta, we're going to see that beta is equal to the inverse tangent of 1/3, and that is approximately 18.435 degrees. Okay, so notice that this is theta, and theta is the acute angle between those two lines. But theta is simply going to be equal to alpha minus beta. Alpha minus beta. If we did the absolute value of this, it really wouldn't matter. It could be beta minus alpha as well. So we're going to leave it like that to illustrate something that I'm going to tell you in a bit. So for now, let's find the acute angle theta. So theta is going to equal the absolute value of, say, 78.690 minus 18.435, and that is going to equal 60.3 degrees. So this would be the answer. That would be the acute angle between the lines. Now, we can generalize saying that an acute angle between two lines is going to equal the absolute value of the difference between the inverse tangent of their slope. So if I have one line with slope m1, find the inverse tangent of that and subtract it from the other line. Same situation, inverse tangent of the slope of the other line. Notice that it doesn't matter in which order, because this is the absolute value. So this gives us a general formula to find that angle in a more direct way. Okay, so now we continue with example 7.18. And in part A, they ask us to find the exact equation of line L1 that passes through the origin. That means there's no y-intercept, or actually the y-intercept is 0, and makes an angle of minus 60 degrees or 120 degrees with the positive direction of the x-axis. Okay, so notice that it doesn't really matter which angle we use here, because these two, or the tangent of these two angles, is the same. And then our reference angles are always with respect to the x-axis. So this here is 60 degrees. So that's our reference angle. And this one is also 60 degrees as a reference angle. Now, obviously, this would be measured normally if we do it counterclockwise to be 300 degrees. Okay? But tangent of 300 degrees or tangent of minus 60 is actually equal then to tangent of 120, and either one of those is going to give us minus square root of 3. And since this one does not have a y-intercept, or rather that it goes through the origin, we have that the equation for L1, so L1, the equation for L1 is going to be y equals negative square root of 3x. So now on part B, which says the equation of the line L2 is 7x plus y plus 1 equal to 0. Find the acute angle between L1 and L2. First of all, let's remember what L1 was. We found it before. L1 is negative square root of 3 times x. And because they want us to find an acute angle between those two lines, remember that the acute angle between two lines is equal to the absolute value of the inverse tangent of one slope minus the inverse tangent of the other slope. So let's just substitute into the formula, and we're going to get that the acute angle between them is going to be the inverse tangent of negative square root of 3 minus the inverse tangent of negative 7. Now, why negative 7? Notice that we would have to rearrange this, right? So if we have 7x plus y plus 1 equal to 0, rearranging y is equal to minus 7x minus 1. So this is the slope. Let's plug this into the calculator, and we're going to get approximately 21.9 degrees, again, rounded to 3 significant figures.